We are Team 38, and this is our presentation for Project 2, the transportation of Antarctic icebergs to Cape Town for freshwater. The objective of this project was to determine the feasibility of providing freshwater to a large population through the use of an iceberg. Specifically, the team had to model the movement of an iceberg from Antarctica to Cape Town, South Africa, and use that model to determine the final cost and all other relevant factors while taking into account the cultural, ethical, and sustainability issues. As a way to break down the project and understand all of its parts, we created a work breakdown structure. We identified the three main categories to this project: research, the model, and the deliverables. From these categories, we continue to work them into smaller categories, as you can see on the slide. Before we could begin with the model, we needed to determine the mechanics of physical and geography of physically moving an iceberg. After our research, we began determining the best route the iceberg would take. On the lower right, you can see a Google Earth image detailing the best route for the iceberg to take from Antarctica to Cape Town based on the ocean currents. A map of these currents is shown in the upper left-hand corner of that map. We also determined the final destination of the iceberg within Cape Town, which is the Fowler Water Treatment Plant, which we'll go into more detail with later. Now that we knew where the iceberg was going, we had to figure out how it was going to get there. To solve this problem, we created a simple functional block diagram. The drawing above the functional block diagram is our solution to the towing system. We determined that by using one or two boats, although only one is pictured, to pull an iceberg that had been surrounded by a flexible geotextile fabric on three sides was the best way to transport this iceberg.
So before diving into the model, we asked ourselves a few questions regarding how we were going to proceed with designing it. Some of these questions included: what shape would the iceberg assume? Would it be a sphere? Would it be tabular? What forces were we going to consider and which forces would we not consider? What would be good values to input into the model? What would be good initial conditions? And which of these initial conditions should be constant? And which of these inputs should change? So other questions we asked were how to make our model time efficient while still being accurate. So what would be a good time step? What are good outputs to calculate, and how is a good way to present them to the client? And then the last question, kind of similar, how can we help visualize these outputs in an intuitive manner to really help the client understand what they're looking at? And so to start this, we created some pseudocode in the form of a flowchart to organize our thoughts and provide a general outline of the model. So the model we created has many distinguishable features and key features. So first off, the model takes three inputs from the user in the forms of the radius of the iceberg, the number of additional boats. So if you want the iceberg to travel faster in a shorter period of time, you would add additional boats, and the number of people that will be dependent on the water. So whether that be the population of Cape Town, or maybe you only want to supply, or maybe you only want to supply half the population because you want to supplement the water that's already there. And then the model also outputs a variety of different useful information, such as the total travel time, the percentage of the iceberg lost, the water duration in the destination, the total cost and revenue of the operation. And then it outputs two different measures of efficiency. So these are volume per cost and profit or loss per 1 million liters of water sold. Finally, the model outputs three different graphs to help visualize the data. So it outputs a pie chart, which shows the cost breakdown, and then two charts that are more related to physics, which are the velocity versus time and the radius versus time graph, just to show what is physically happening to the iceberg over time. The model also accounts for mass loss due to the thermal transfer in the form of convection. So that was one thing that we thought was useful and a good thing to add. And the UI is simple to interact with and only takes about 5 seconds to run, so it is very efficient. So there were many assumptions that we had to make while creating this model in order to actually be able to do these calculations. So these include, but we're not limited to, things such as assuming that the iceberg was spherical. We didn't account for the Coriolis force because we just assumed that there would be no rotation due to the net. That kind of simplified some things. We assumed that the force on the tow rope would be equal to the force on the tugboat. This is a big assumption that we made. We also assumed that the towing force only acted in the horizontal direction, which we know is not totally true, but it really helped to simplify the calculations and created a pretty good estimate. We also assumed that the iceberg melting due to heat transfer came solely from the water and not from the sun. And so we assumed that that rate applied to all sides of the iceberg, even though we know that the top would not melt at the same rate at as the bottom. And we also assumed that the path taken and that the initial location of the iceberg was about the same every single time.
To calculate the efficiency of a model, we decided to use the Cottas method. Using this method, we concluded that the amount of people that are dependent on the water is the most sensitive factor in the model. The reason for this is because the price of processing is a significant factor, and if less people use the water, we will have to process over a longer period of time, which costs us more money. However, if we were to consider just the model for Cape Town, we could hold the number of people dependent on the water constant, meaning that the most sensitive factor would then be the radius of the iceberg by a factor of almost 3. So using the optimal inputs, we calculate the cost efficiency to be 1,928.5 liters per dollar spent, and the profit efficiency to be $81.50 per 1 million liters sold. So the project will cost us a total of around $38 million and have a revenue of around $44 million, giving us a profit of $6 million. And the larger the iceberg is, the less percent of the original mass would be lost. However, this had to be balanced with the cost of having more boats and using more fuel. So having an iceberg of radius 296 meters was chosen because that's the largest mass that can be towed by one towboat, which means it has the best profit efficiency ratio.
As we mentioned before, we also had to consider the ethical, cultural, and sustainability issues while creating our model. Cape Town's current water system consists of water supplied from rainwater and groundwater, and they employ over 22,000 people in the water sector. Our current model focuses on using the infrastructure already in place in order to lower costs, keep jobs, and minimize the overall interruption to society in Cape Town by the water from the iceberg being a supplement rather than a replacement. The water will be processed in a major plant that supplies 31% of the town's water. The environmental impact was also a very big consideration, and we had to conclude that the effects would be unknown because the melting iceberg can affect the temperature of the water extremely and potentially impact the marine life in the area, especially species that are very sensitive to changes in water temperature. Overall, Cape Town seems to be open to more sustainable water choices, and they have undergone major changes to their water use and system in recent years. So we concluded that they would likely be open to using this system to supplement their water. Some limitations in our model could be improved upon. This would include changes to the model, allowing for more variation in iceberg size and shape, as well as changes in tug force as the iceberg melts. The model would also allow input coordinates for starting point and destination of the iceberg, as well as data from current weather databases to more accurately predict conditions along the route and therefore changes in the iceberg travel times. The model would also incorporate things that had to be left out originally, such as Coriolis force, gradient force, and some more specific costs. In conclusion, is this feasible? Specifically in Cape Town, icebergs could provide so much fresh water to an area struggling to find enough, but the startup cost for a project like this would be enormous, and many of the materials, such as the boats, are difficult to locate or produce, which makes them more expensive, among other things. Physically moving an iceberg as large as we have suggested is extremely difficult and could be dangerous for both the people moving it and the marine life in the areas it travels through. Considering that this has never been done before, there is not enough research, and even if there was, we would not be able to accurately predict the effects of moving an iceberg from place to place. So theoretically, icebergs can be used as a freshwater source. But is it practical? Not really, especially once you consider all the factors and the necessary inaccuracies due to the amount of assumptions that were drawn over the course of this project.
The model consists of 4 different files. The first file, which is seen here, is the main file, which calls the different functions and does all the calculations. The 3 other files, which you can see here, are all functions which have specific tasks and help reduce the amount of code in the main model. So the main model starts off by requesting inputs from users, the radius of iceberg, the number of the boats, and the number of people that are dependent on the water that is being brought in thousands. Then, all the initial conditions are set, and these are things such as the time step, the number of boats, the towing force, the initial velocity, which is of course 0, and other things like that. Also, arrays are initialized in order to be able to add values to them later so that different things such as velocity and radius can be graphed using the MATLAB functions. And then, so the first real part of the model is here, and this is where the values for the South Atlantic current are initialized. So you can see the temperature is set to 3 degrees Celsius for the water velocity, or the current velocity, is 0.23 meters per second, and the air velocity is 9 meters per second, just for example. And so this big while loop here is where we iterate through the different time values. So time values while the distance is less than around 3,500 kilometers. That's the distance that the boat will be in the South Atlantic current. And so it's iterating through these time values and calculating every single time it goes through the new mass, the new radius, and the new forces, and that'll be able to calculate the velocity that is at each iteration and other things like that, so that at the end of the day, you're able to approximate this function. And so these values are also added to arrays so that they can later be graphed. And this is just the same thing, but for the Benguela current, so you have all the values initialized here, and then you have the while loop down here. So after all the calculations are done, we take all those iterated values and we do final calculations with those final values. So for example, the total amount of days is the current time divided by 3600 divided by 24 if you want to put it into days, from seconds to days. And then we do other calculations such as percent loss, and then all the cost calculations, and then the efficiency calculations, which are seen here. Finally, we graph different parts of the data. We graph the time versus velocity, or velocity versus time, and radius versus time, and we also make a pie chart to display kind of the price breakdown of this project. So now I will run this script for you. So the first thing the script asks for is the iceberg radius, which I'm going to put the default for. Then it asks for the number of extra boats, which I'll also use the default. And then it also asks for the number of people dependent on water in thousands, which I will also input the default for, which is 1,300 or 1.3 million people. It will then calculate all the values, and this takes a few seconds. Okay, so once this is done, the model outputs a variety of different graphs. So you can see here, this is the total price breakdown, the pie chart of total price breakdown by category, by the main categories, and then you can see the velocity versus time and radius versus time graphs. You can also see in the console the different outputs, the statistics, the numbers. So you can see the total travel time, the percent of iceberg mass lost, and then the water duration, or how long the water will last the people in your destination. Then you can also see the total revenue, cost, then the net profit or cost, and then the two forms of efficiency, the cost efficiency and the profit efficiency. So this is how our model works. You can see that it's very efficient, and it's also easy to be customized. And although it is not perfect, I think it's a very solid start and does a good job of estimating this problem.